In this video, we're going to have a look at the binomial theorem and the binomial series and see what we can use them for. Now, the binomial theorem looks like a plus b to the n is equal to the sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. Or you can also write it with the same sum and the same n choose k, but instead have a to the k, b to the n minus k. And either works. Now, the important thing in our binomial theorem is this power of n, where n has to be an element of natural numbers. So something like 1, 2, all the way up. And n appears a couple of times on the right-hand side. So the first thing is that when we sum from k equals 0 to n. And the second time it appears is when we're doing our n choose k. And finally, it also appears in the exponent of either our a or our b. The next thing that we need to think about is this n choose k. And just let's remind ourselves what that's all about. Well, n choose k is n factorial over k factorial n minus k factorial. And if we need to remind ourselves how to find that, we use Pascal's triangle, which looks like this. We start with a 1, and then we have in the next row 2 1s. Our next row is going to have 3 entries. Always the first entry is a 1. The second entry is going to be the sum of the 2 above it, so that's going to give us a 2. And then we finish off with a 1. And our fourth row is going to be a 1. Now we sum the 2 above it, so that gives us a 3. The next entry we sum the 2 above it, which gives us another 3, and we end with a 1. And we start again for our fifth row. We've got a 1. Now we have a 1 plus a 3. That gives us a 4 and a 6 and a 4 and a 1. What do these mysterious numbers give us? Well, for the various values of n, they give us n choose k. So our very first row we have n equals 0. Then we have n equals 1, n equals 2, n equals 3, n equals 4. So our rows tell us about the different possibilities for combinations with n. And if we go along the diagonals, we have the options for k. So for k equal to 0, we use the first diagonal. Second diagonal gives us k equal 1, k equals 2, k equals 3, and k equals 4. So now if I want to know, for example, what is 4 choose 2, well, then I'm going to look at n equals 4, and I'm going to look at my k equals 2, and that tells me it's 6. And so that gives me a quick way of working out, but if we were to go back and check using our formula, that would give us 4 factorial over 2 factorial, 4 minus 2 factorial, so that's 4 times 3 times 2 times 1 over 2 times 1 times, and 4 minus 2 gives us a 2 factorial, so that's another 2 times 1. So our 2's cancel. We've got a 2 in the bottom, which will cancel one of the 2's in our 4. And we finally have 2 times 3, which is 6. So we get the same answer either way, but knowing Pascal's triangle can be quite handy. So what do we use this binomial theorem for? Well, we use it for expanding out polynomials that we wouldn't necessarily want to do by hand. For example, we might have something like x plus 2 to the 3, and we could multiply that all out, but it would be a bit of a pain. But we can use our handy binomial theorem. So what we're going to do is we're going to think of x as our a and 2 as our b, and then the binomial theorem tells us that our answer will be the sum from k equals 0 to 3 of 3 choose k. Now our a is actually going to be an x, so that's going to be an x to the 3 minus k, and our b is our 2, so that's going to be a 2 to the k. And if we write this out all in excruciating detail, we know that we're going to sum from k equals 0 to 3, so we should have 4 terms, and it's going to equal 3 choose 0, x to the 3 minus 0, which is just 3, and 2 to the 0, which is just 1. Then our next term is going to be 3 choose 1, x to the 3 minus 1, so that's going to give us a 2, and that's going to be a 2 to the 1, so that's times 2. Our third term is going to be 3 choose 2. That's going to be x to the 3 minus 3. Sorry, x 3 minus 2, so that's going to be x to the 1, and that's going to be a 2 to the 2, so that's going to give us a 4. And our final term is going to be 3 choose 3, x to the 3 minus 3, which is 0, and 2 to the 3, which is 8. So now if we use our Pascal's triangle, so we're looking at the n equals 3 row, we can go ahead and fill in our coefficients. So we've got an x cubed, because 3 choose 0 is 1. 3 choose 1 is 3, so we've got a 3 times 2, which gives us a 6x squared. We've got 3 choose 2, which is also 3 times 4, which is going to give us 12x. And then finally we've got a 3 choose 3, which is 1, times x to the 0, which is also 1, times 2 to the 3, which is 8. So we end off with our polynomial, which is the expansion of x plus 2 to the 3. Now let's go back to the binomial series and have a look at that. So our binomial series looks like 1 plus x to the alpha is equal to, okay, a little bit more space over here, 1 plus, so we have a sum again. Now this sum, notice, goes from k equals 1 all the way to infinity, and then we have alpha minus 1, alpha minus 2, a whole bunch of brackets until we get alpha minus k plus 1, x to the k, and this is all over k factorial. So the things to notice about the binomial series is that our exponent here is an alpha, whereas for the binomial theorem it was an n, and we use a slightly different notation because this alpha can be any real number. So notice that we have a slight difference here. In our binomial theorem, our exponent has to be a positive integer, but for the binomial series, our exponent can be any real number. The next difference to notice between the two is that for our binomial series, our sum goes all the way to infinity. So this gives us an infinite sum. Whereas for our binomial theorem, it was finite. We only went as far as n. The next thing to have a look at is the coefficient of x to the k. Now notice that in the numerator of this fraction, we've got alpha appearing a bunch of times. We've got a number of brackets multiplying each other. So we have alpha times alpha minus 1 times alpha minus 2, and we keep going alpha minus 3 all the way to alpha minus k plus 1. So one of the things that it takes a little while to work through sometimes is how many times do we subtract 1 off from alpha? When do we stop? And the easiest way to see this is to work through an example. So let's suppose that we're looking at 1 plus x to the 5. So our alpha is equal to 5. And we want to think about the values of the coefficients. So what we're going to do is we're going to look at what's the coefficient when k equals 1. So that's our lowest value. When k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6. So that's our k value. And the next thing we're going to think about is we're wondering what is this smallest bracket that we multiply by. So what is alpha minus k plus 1? Well, if k is equal to 1, then we've got alpha, which is 5, minus 1 plus 1, so that's equal to 5. So our whole coefficient, which is alpha minus 1, alpha minus 2, all the way down to alpha minus k plus 1, has to start at alpha, which is 5, and end at alpha minus k plus 1, which we've just worked out is 5. So in fact, that coefficient is just 5. If we have a look at k equals 2, we've got 5 minus 2 plus 1, which is 4. So we have to start our whole coefficient at 5, and we have to finish it at 4. So we go alpha minus 1, that's 4, and we're done. If we look at k equals 3, we've got 5 minus 3 plus 1, which is equal to 3. So we start at 5, we have 5 minus 1, which is 4, times 5 minus 2, which is 3, and we finish. And we can keep on doing this. So if we have a look at k equals 4, we have 5 minus 4 plus 1, which is 2, and you'll quickly see our coefficient is 5 times 4 times 3 times 2. And now if we look at k equals 5, then we've got 5 minus 5 plus 1, which gives us 1, and we'll have 5 times 4 times 3 times 2 times 1. So if we have a look at the next term, which would actually be k equals 6, now we have 5 minus 6 plus 1, which is equal to 0. So our terms go 5 times 4 times 3 times 2 times 1 times 0, and that whole thing is going to be equal to 0. And notice that if we have any higher values for k, for example 7, then our alpha minus k plus 1 would give us a minus 1. So we'd have 5 times 4 times 3 times 2 times 1 times 0 times minus 1, and that's still going to be 0. And any later ones are always going to have a 0 in. So for alpha equals 5, our binomial series is actually finite. It only has 5 terms. So let's just take a moment to write those out. So if we were to expand out 1 plus x to the 5 using our binomial series, what we'd get is 1, because don't forget that 1, plus, and now we work through our sum. So when k equals 1, we have 5 over 1 factorial, which is just 1, times x to the 1, plus now we have 5 times 4 over 2 factorial times x squared, plus 5 times 4 times 3 over 3 factorial x cubed, plus 5 times 4 times 3 times 2 over 4 factorial x to the power 4, plus 5 times 4 times 3 times 2 times 1 over 5 factorial x to the 5. And what you'll notice about this last term is that we actually have 5 factorial divided by 5 factorial, so we end up just with x to the 5. If we do a little bit of cancelling, we get that 1 plus x to the 5 is 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the 4 plus x to the 5th. And you'll notice that was a lot quicker than multiplying out 1 plus x 5 times. Now, we won't always have just a finite number of terms if we're using a binomial series. So, for example, if we want to have a look at when alpha is equal to minus a half, what will our various coefficients be? Well, we need to worry about our k value, our alpha minus k plus 1, and then our alpha minus 1, alpha minus 2, all the way through to alpha minus k plus 1. So let's have a look at what that table looks like for alpha equals minus a half. Well, if k equals 1, then we have minus a half minus 1 plus 1, which gives us a half. So our coefficient there is going to be minus a half. When k is equal to 2, then we're going to have minus a half minus 2 plus 1, which is minus 3 over 2. So our coefficient is going to be minus 1 over 2 times minus 3 over 2. And you can see that if we carry on with k equals 3 and so on, we're just going to carry on adding more and more terms when we're never going to have a zero bracket. So this gives us an infinite polynomial, unlike the case above. So I want to finish off by just showing you that anything you can do with the binomial theorem, you can do with the binomial series. So let's do the same example that we did with our binomial theorem, which was x plus 2 to the 3. Now you might be wondering how we could possibly do this, because if you remember, our binomial series needs something of the form 1 plus x to the alpha. But we can do a little bit of working to get our x plus 2 to the 3 in that form. So the first thing we're going to do, just to make things easier, is I'm going to switch the order I'm adding. So I'm going to say 2 plus x all to the 3. So now that looks a little bit better, but we've still got a 2 here, and that's not good because in our binomial series we need a 1. So what I'm going to do is I'm going to write 2 plus x as 2 into 1 plus x over 2. So I've taken out a common 2, and we need to have that whole thing to the power 3. But really this is the same as saying 2 to the 3 times 1 plus x over 2 to the 3. And now things are beginning to look quite useful. So if in our binomial series we're going to replace the x in our binomial series with an x over 2, then what we can do is we can say, well, our x plus 2 to the 3 is equal to 2 to the 3, and now we're going to replace this 1 plus x over 2 to the 3 with our binomial series. So we have our alpha is equal to 3, and wherever we see an x in our original binomial series, we're going to put in an x plus 2. So what we've got to have is a 1 plus our sum going from k equals 1 to infinity of alpha minus 1, all the way down to alpha minus k plus 1 over k factorial. And then in our original we had x to the k, but remember we're replacing our x with an x over 2, so we have an x over 2 to the k. Okay, so far so good. So now we can go through and we can work out each of these terms. So we've got now 2 to the 3 is 8, and that's going to multiply in our 1 plus. Now when k is equal to 1, then our coefficient is just going to be 3 times x over 2 to the 1. Then when k is equal to 2, we're going to have a 3 times 2 over 2 factorial, x over 2 to the 2. And when k is equal to 3, we've got a 3 times 2 times 1 over 3 factorial times x over 2 to the 3, and any further terms are equal to 0 by the same reasoning that we saw when we took alpha equals to 5. So if we do a final last little bit of working, and we can see we've got, multiplying in, we've got our 8 plus 8 times 3 over 2 times x plus 8 times 3 times 2 over 2, because 2 factorial is 2. And now we've got it 2 squared, so we've got a 4, and then x squared. And then we've got an 8 times 3 times 2 times 1 over 3 factorial, and we've got a 2 cubed in the denominator, which is also an 8, and that's going to give us the coefficient for our x cubed term, and all the rest are equal to 0. And you do a little bit of multiplication, and you'll find you get 8 plus 12x plus 6x squared plus x cubed. And you'll notice that if we go back and have a look what we worked out originally using our binomial theorem, we've got the same thing. So you can get the same answer both ways. So you can pick whichever way unless it's specifically stated which techniques to use. Personally, I find binomial theorem a little easier for this kind of thing, but if you want to use the binomial series, there's no problem. You'll get the same answer. Now, you might be wondering how all this links to Taylor series and Taylor polynomials. Well, if you were to work out the Taylor series for 1 plus x to the alpha for a equals 0, you would actually get the binomial series. You can check that for yourself. And just a bit of recap, you might also sometimes see the Taylor series for a equals 0 as the Maclaurin series. And the binomial theorem is just really a special case for alpha, a natural number will give you, and a little bit of tweaking, will give you the binomial theorem. So this is how they all match up. So everything that we've been doing up to now is really all about writing something as a polynomial. So you'll have seen in what we've just been doing, we've expanded, for example, x plus 2 to the 3 as a polynomial, which is exactly what we did with the Taylor series. So now I want to have a look at a fairly typical question which asks us to find the coefficient of one of the powers of x in the expansion of a particular polynomial. So we're not being asked to find the entire expansion of x squared minus 2 over x to the 4. We just want to find the coefficient of the term x to the 5. So I'm going to do this in two ways, just to reinforce the idea that you can use the binomial theorem or the series when you have a positive integer power that you want to expand. So let's look at this the first way using the binomial theorem. Okay, so we're having a look at x squared minus 2 over x to the 4. So let's just make sure that we get everything right. So our x squared is going to behave like our a. Our minus 2 over x, so be a little careful here, don't forget to include the minus sign, is going to be our b. And our n is going to be equal to 4. So if we plug this into the formula, then what we've got is we've got the sum from, now binomial theorem goes from k equals 0 to n, so that's going to 4. And then we have 4 choose k, and then we have our a, which in this case is x squared, to the n minus k, and then we have our b, which here is our minus 2 over x, and that's going to be raised to the power k. So let's do a little bit of cleanup here. We can't do anything with the sum, so that's k equals 0 to 4 of 4 choose k. But now we have an x squared raised to the 4 minus k. So remember, our exponents multiply. So we actually have an x to the 8 minus 2k. Now I'm going to separate out my b terms. So I've got a minus 2 to the k. And then I've got a 1 over x. So that's really x to the minus 1, all raised to the power k. So I have an x to the minus k. I'm doing this because I want to combine all the terms that have x's in them. So if I go ahead and do that, I have k equals 0 to 4, 4 choose k, and now I've got, let's just put my minus 2k in to get that out the way. Now I've got an x to the 8 minus 2k minus k, so that's going to give me an 8 minus 3k. Now what we want is the coefficient for whatever value of k makes x to the 8 minus 3k x to the 5, because we've been asked for the coefficient of x to the 5. So what we need to do is find out which value of k gives us 8 minus 3k equal to 5. And if we work through that, you'll see that we get k is equal to 1. So that tells us that when k is equal to 1, we'll have x to the 5, and if we work out 4 choose 1 times minus 2 to the 1, then we'll get the coefficient that we want. So let's just do that quickly. So we have that our coefficient of x to the 5 is 4 choose 1 times minus 2 to the 1, and that equals minus 8. So there we've worked out the coefficient of one particular power of x in our expansion. So now we're going to work through the same example, but this time we're going to use the binomial series. So the first thing we need to do is we need to write our x squared minus 2 over x to the 4 in the format that we can use for the binomial theorem. I'm going to write it as x squared minus 2x to the minus 1 to the 4. And then what I'm going to do is the same trick that we played previously. I'm going to take out a common x squared, so that I have a 1 minus 2, and then I have an x to the minus 3. And all of that is raised to the power 4. And if I write that out a little clearer, then I have x to the 8 times 1 minus 2x to the minus 3, all to the power 4. And now we'll see that this 1 minus 2x to the minus 3, all to the 4, is what I can use my binomial series on, where I'm going to have my alpha is 4, and my minus 2x to the minus 3 replaces x in my original version. Okay, so if I write this all out, then I have x to the 8 all times, and now I'm writing out my binomial series. So I have 1 plus the sum from k equals 1 to infinity of 4 times 3 all the way down to 4 minus k plus 1 all over k factorial. And then I have to replace my original x to the k with minus 2x to the minus 3 all to the k. So if I write this out a little more clearly, I've got an x to the 8 times 1 plus k equals 1 to infinity, 4 times 3, all the way down to k, 4 minus k plus 1, all over k factorial. And then I have a minus 2 to the k times an x to the minus 3k. Okay. Now the thing to remember is that we want the coefficient of x to the 5, and any term in my binomial series is going to be multiplied by x to the 8. So for x to the 5, I need that x to the 8 times x to the minus 3k is equal to x to the 5. And the equation there becomes x minus 3k equals 5. And so, as we've seen before, k equals 1. So now that we know that we're looking for the coefficient when k is equal to 1, we have that the coefficient when k is equal to 1 is, well, let's just check. 4 minus 1 plus 1 equals 4. So our coefficient is 4 times minus 2 to the 1 over 1 factorial, which equals minus 8. And that's the same answer that we got using the binomial theorem, just via a different version. So anything you can do with the binomial theorem, you can do with the binomial series, but you can do more with the binomial series because it allows you to have any real number, although at the moment we've just been using positive integers. So now we're going to do one final example, which is that we want to write the first three terms of the expansion of 1 minus 2x all to the minus a half. So this is one case where we can't choose which theorem to use. We only have one option because we've got an exponent that is a negative and it's not a whole number. This tells us that we're going to have to use the binomial series. And so we're going to have our binomial series with minus a half is our alpha, and we're going to replace x in the original with minus 2x. So if we go ahead and do that, then we have 1 minus 2x to the minus a half is equal to 1 plus, and we have our sum from k equals 1 to infinity. And we have minus a half minus 1, which is minus 3 over 2. And we have minus a half minus 2, which is minus 5 over 2. And we keep on subtracting until we get minus a half minus k plus 1. And then we have minus 2x, which replaces our x in the original, all to the k. And don't forget to divide by k to the half. We want the first three terms. So here we go. Well, our first term is always going to be 1. Then our second term is when k is equal to 1. So let's just make a note. This is k equals 1. When k equals 1, our minus a half minus k plus 1 goes as far as minus a half. So that's just going to give us minus a half over 1 factorial times minus 2x to the 1. So there we've got our second term. And for our third term, our minus a half minus k plus 1 is going to go to minus 3 over 2. So we're going to have minus a half minus 3 over 2 times minus 2x to the 2 all over 2 factorial. So that's our k equals 2 term. So there are our first three terms. We can tidy that up a bit. That's 1 plus minus a half times minus 2x plus minus a half times minus 3 over 2 times minus 2 all squared, x squared all over 2. And that's good enough. So this is an example where we had to use the binomial series. We couldn't use the binomial theorem because we had a non-integer exponent. And there are other examples on YouTube that I've done as well.